Example of a more in-depth graph algorithm beyond the simplicities of things like A star or Dijkstra for finding the shortest path, looking at what we can do modeling this graph and trying to find a way to partition or label the contents of this graph. Let's take a look. Let's say we have some information about some staff, like some sort of grouping of these staff, and we want to model this as a graph of some sort. So we can pull this information into NetworkX and we can take a look at the nodes and the edges. And we can even take these nodes and we can visualize what they look like. We can visualize all of the connectivity between all of these different staff members that we have. And when we look at this, and whenever we look at a graph, and whenever we try and solve a graph algorithm, one of the things that we should really think about is, what do the nodes really mean? What do the edges really mean? What does this connectivity signify? Clearly, this is a cyclic graph. Clearly, this is a non-directed graph. So whatever this signifies is a bidirectional or reciprocated sense. And what the nodes mean, that's pretty obvious. It's a human being. It's a physical entity. Well, what if I told you that the connectivity here represented who is not allowed to be in the same room as somebody else, who's not allowed to work? Maybe we're at a secured or classified site and we can't have two of the stakeholders for somebody in the same room at the same time. Or maybe Alice just doesn't really like working with Charlie. We can't put them on the same team together because we know they're going to fight because Alice keeps talking about why she loves list comprehensions. And if Charlie has to hear about a list comprehension one more time, he's going to throw a fit. 4 loops, nested 4 loops, that's all he can stomach. Don't tell me about the 5-level deep nested comprehension. And so maybe our goal is to figure out how to label each one of these nodes in terms of how we can align each one of these people with teams, knowing that there are certain people that we cannot put onto the same team for whatever reason. And so what we'll say is this connectivity represents who cannot be partnered up with somebody else. Alice can't be partnered with Dana, Evan, Bob, or Charlie. And you can see that this makes it a little bit tricky because who can she be partnered with? She may be connected to everybody. She may need to be in a group all by herself. Those list comprehension opinions are really controversial. Graph coloring is the idea that we take these nodes and we can assign a color to each of the nodes. And oftentimes when you look at this word coloring mathematically, well, it often means some sort of arbitrary labeling. If you go to Wikipedia and you look at the diagram for graph coloring, it'll show you that the whole idea of graph coloring is you take some nodes that have some connectivity and you find some way to put a label, in this case a color, on these nodes, and there could be multiple different ways that you might do this. And you do this in such a fashion that no 2 connected nodes can have the same label, can have the same coloring. It turns out this is very easy to do in NetworkX. And so if we take our groups, we can use greedy color directly from NetworkX, and it can give us a coloring for this graph. And let me show you what it gives us as the output. It tells us, okay, Alice is going to be on team 0. Bob and Dana can work together, and Charlie and Evan can work together. It gives us this coloring, and we can even see what the groups are: Alice, Dana, and Bob together, Evan, Charlie, or we can visualize this and we can see how this has partitioned our data set. We can think of graph coloring as a mechanism by which to partition the nodes subject to the rule that no 2 connected nodes can be in the same group. And applied to our who can't stand to work with anybody else, well, I'm sorry, Alice, you're going to have to be in the group project all by yourself. But Dana, you can work together with Bob over here, and Evan and Charlie can work together without any problem. They're not directly connected to each other. When we talk about this kind of problem, we can also talk about this kind of problem from the perspective of asking whether or not these nodes have a particular orientation with regards to the edges, if this graph happens to be bipartite. When we talk about the nodes of a graph, it is not the case that the nodes have to be a homogeneous entity. You might think, oh, in the previous example, the nodes were all staff members. But what if the nodes were a mix of the staff members and the jobs or the roles that they're interested in doing? And so here we have 4 roles, A, B, C, and D. Maybe one is front end, one is back end, maybe one is finance, one is HR, and everybody has registered what they want to do. Bob and Charlie are happy to do job A, Alice and Charlie are happy to do job B, and Bob's the only one who's willing to do job C. I think that's what he's going to get assigned to doing. And Charlie and Dana are willing to do job D. We can create a NetworkX digraph with these entities where these entities are not homogeneous. They don't all represent people. Some of the nodes represent people. Some of the nodes represent jobs that they might do. And the connectivity is I'm willing to do this. Now this is bidirectional, so I guess it's either I'm willing to do this or I'm willing to have this done by me. But you can see Alice is connected to B, as is Charlie. A bipartite graph is a graph that can be split into two groups of nodes where all of the groups of nodes from one side are connected to all of the groups of nodes from the other side. And in this case, what it can be used to solve is there a stable matching? Bipartite graphs come up very often in the stable matching problems. But one of the things that I might do at the immediate is, before I even look at what the matching is, I might say, have I surveyed enough people? Is it the case, clearly, if nobody answers the survey, or let's say that Alice answers the survey, I can ask, is this bipartite? And let's turn off our visualization. And this is bipartite tells me, is there a possible stable matching? And you can see, if we had surveyed people like this, there absolutely is. If I make it so that nobody has surveyed C, but I add C into this, I'll have to add this in manually. I shouldn't see it by, I see a bipartite. Let's see if we can do this. We might have to force this in some way. But the idea is we can ask whether or not there's a possible stable matching here, and we could use that information in order to determine whether it's the case that we've surveyed people enough or will they poke people. Can you get one more person to sign up for job B just to make sure that we can allocate this? If this is bipartite, we can ask for the sets, how it would partition this so that every node is connected to every other node. And it'll say, oh, you partition all the jobs, A, B, C, and D, and you partition all the people, and that's exactly what we look for. And we can even ask for the maximum possible matching, which job goes to which person. Now you can see here, this is giving us the bidirectional. It's saying job D is for Dana, but also if you look at this, you can see Dana goes to job D. But if we take this data and we redraw the graph based on that data, we can see exactly how it's going to align and associate these. Alice gets job B, Dana gets job D, Bob gets job C, Charlie gets job A. You can think that bipartite matching is another way for us to segment this data based on connectivity, again, very similar to coloring. And in fact, there's a close relationship between all of these ideas and even ideas like finding clicks in a graph. In general, when we look at these kinds of problems, you might not have an intuition that you could use a graph to solve it in this fashion, but here you can see exactly how a graph can be used to solve this problem itself, to figure out what job should go to what person.